did method of sections on one example, right? Let's look at a second example problem. Truss looks like. The reaction points are at the bottom, and here's the roller here, and the pin here. We have horizontal load applied here, 12 kips. Vertical load of 30 kips here. Vertical load of 18 kips here. Spacing horizontally, he weighs 12 feet. And vertically, there are different heights. 9 feet, 9 feet, and 16 feet. This is a roller, so we have reaction A. And then the pin, there's R sub dx and R sub dy. We're going to solve for various, we'll take different section cuts and see how we would do that in a problem like this. We have section 1-1, let's say just to the right of F and H. Right, so that's a vertical cut all the way through the structure. Section 2-2 is just to the right of E and H, so it's a diagonal cut here. Notice in section 1-1, we're going to need to include the 18 kips. In section 2-2, we're going to need to include that 12 kips here. That arrow here is right at the joint. So it's just to the left of the dotted line, right? And then section 3-3, we'll take instead of a vertical or a diagonal cut, we'll take an exactly horizontal cut through the structure right above J. Here's J. And C. So this is 3-3. And we'll see, in that case, we're gonna have to include all these reactions in that. So sections 1, 1, and 2, 2 are just to the right of the joint, so I'm gonna include for section 1, 1, just this part of the structure. Section 2, 2, I'll include everything from the left up to that point. The section 3, 3, it's just above J and C, so I'm gonna include the bottom part of the structure, so that will have the reactions too. So first we work with the reactions, of course. Summation of forces in the x is 0. This is a roller. Any applied forces up above the reactions have to be taken out down at the reaction. There are no reactions up at the higher part of the structure. So we have, you can see there's a horizontal force applied there. So in the reaction I've sketched that way. That's why I sketched it that way. It's okay, I could sketch it the other way. It would just come out as a negative, which means it's still that way, right? So I have R sub Vx is 12 force. This is 12. So you look at it and see, oh, that's what's preventing the structure from just sliding to the left. There are different types of possible movements if there weren't reactions. But if we didn't have a pin here holding us back, this is trying to push the structure that way, right? This pin is literally stopping it, no movement at all. At that location, 0 movement and slight deformations throughout the structure, but this is preventing it from just moving, dynamically the whole structure. So that's 12 kips this way, so the structure feels this 12 kips pulling that way, and it feels 12 kips pushing that way. And then I should also point out, at this reaction, that reaction is preventing the structure as a whole from just continuing to displace 20, 30 feet, whatever. So, but that reaction point also has, by definition, absolutely 0 displacement horizontally. Where the load's applied is displacing, but not much, maybe half an inch or something like that, until the whole structure reaches equilibrium. So we haven't talked about that, we're not going to in this class, but we can also calculate local displacements for the whole structure. But by definition, even when you do that, this point still doesn't move, right? Because that's fixed in terms of translation. And vertically also, same with this one. Now horizontally, this might move an inch or so for the whole structure as it displaces, as it strains, stresses, and deforms. It's not going to go 1,000 feet, which is what we're preventing by providing the pin. But by definition, even if you put this in a computer program, what will come out is you'll get these small displacements throughout the structure as it reaches equilibrium, but that location will say 0, 0. And this one, horizontally, there'll be a small displacement due to the deformations within the structure, but vertically this will be 0. So wherever there's a reaction, in the direction of the reaction, there's 0 displacement. That's why a reaction is shown now. And then you can see I've drawn this down. Everything applying a force on the structure, the 12 kips to the left and the 18 and 30 kips down, all of them are tending to have this thing rotate about A, wanting to lift up. So this reaction is holding it down, and you can see by taking moments about A that all of these applied forces are causing, taking a look at an axis coming out of the page, counterclockwise movement. And so this reaction times this distance, that has to be in that way, that provides a countering clockwise movement, right? When you're looking back. So if reaction B, let's say there's a horizontal reaction, prevented the structure from displacing, but it also needs this vertical reaction to prevent it from rotating about A and just lifting, falling over, right? Otherwise it would just pivot about this point. And then there's this reaction here. I've drawn it this way. We'll see if that's correct. It should be. It depends on the magnitude of this. Okay, so those are in terms of our reactions. Let's solve for the rest of them with some moments about A. So I have RCBY multiplied by 12. So that's a clockwise moment at A equals the 3 contributions to the moment going counterclockwise from the 3 applied forces. So 2 are vertical, 1's horizontal. 30 times this force times the distance to A, the normal distance, which is 24, plus 18 times this normal distance, which is 12. 18 times 12, counterclockwise, plus 12. 12 multiplied by what? 34. Is that right? It's 12 times multiplied by the vertical distance. 16 plus 9 is 25, and another 9 is 34. So I get a positive number, 112 gives. So that means that the initial direction I drew it is correct. If I did this and I came out with a negative, it just means it would be opposite to the way I drew it. I wouldn't redraw it, because then the prior equation is no longer correct, right? But I would add another arrow if it came out to be negative, and then draw it the other way with the value next to it. You get into a lot of trouble if, let's say we didn't get a negative, but let's say we did get a negative here, and then if you go and erase this, and then change the sign, draw the arrow the other way, and it still says R sub dy, then this equation is no longer valid, right? So you get into, it becomes messy. So you have to be very careful. Okay, so summation of forces in the vertical direction is 0. I'm doing that just to solve for R sub A. That's the only unknown reaction. 3 reactions, 3 equations. And you can see R sub A is up, everything else is down, including this reaction, for the reasons that I gave. So I have 30 plus 18 plus 112 has to be, there's nothing else in the vertical direction. So I have R sub A, which only has a vertical component. That's why I'm not saying R sub A y, because it's the only one. R sub A equals 112 plus 30 plus 18. Those are all of our reactions. we're taking the section cut just to the right of F and H. So I'm including, because to find it just to the right, not just to the left, we have to include the 18 kips. So make sure it's applied directly at H. And we also have 30 kips down at G. Now I'm solving, so I cut through FE. So I have three forces, F of FE, F of HE, which is at an angle, and F of HI. This is that angle theta that's shown there. You can see that the tangent of theta is 9/12. It's 36.9 degrees, less than 45 degrees. So it's this geometry, this over this. So let's solve for F of FE first. Summing moments about H is 0. In that case, we have three forces going right through H, so they don't need to be included in the summation. We have F of HE, F of HI, and the 18 kips all going right through H. So they have no contribution to the moment about H. And therefore, the only moments are F of FE, from F of FE, and the 30. So we can just write it directly. F of FE times 9 equals 30 times 12. This is 40 kips. I drew it as tension, and it's positive, so it is tension. Okay. So you can see this type of a problem. It's very easy to have everything kind of coming together at a point like that. We can take a cut here and then solve for F of FE. Right? There was only one other force that was providing positive moment. And so stepping back a little and just looking at it, you can see it's a balancing point, right? There's a moment from this, and this force times this is balanced by that force times this, right? The moment that way and the moment that way, about that point. Only those two things are contributing. So they're in balance. Summation of forces in the y is 0. Now we do have to include not F of FE or F of HI, because those are horizontal. There's no contribution in the vertical direction. So in this case, so for each part that you look at, you have to consider these things. So vertically, we have the 18 and the 30 that are in the picture. And then we have not the full F of HE, but its vertical component. So that's why we have to take the sign of that. So we have F of HE multiplied by the sine of theta. Cosine is horizontal, cosine gives me the vertical part, so that has to equal everything else going the other way. So that's up, and then 30 plus 8. So F of HE is 80 kips in tension. How do I know it's tension? Because I drew it that way, right? And it's positive. It came out consistent. I could have drawn the other way. If I drew it with an arrow going into joint H, that would be saying that it's in compression. And then if I did that, I would have come out with a negative here, which means that it's actually tension, just like I drew it down.
So would it be safe not to draw an arrow until we figure out?
Say that louder.
Would it be safe not to draw an arrow until we figure out if it's going to?
No, you have to draw an arrow because then you can't sum forces or moments or anything. If you don't draw an arrow, you have no idea how to sum forces. You have to draw it one way or the other, and then see what you get. Yeah, if you don't draw an arrow, you have nothing, except a line. Because when I go to, for example, sum forces vertically, in this case I said this equals that plus that. So the vertical component, because I drew it that way, right? So I have a force up. If I didn't have an arrow, in other words, is what you're saying, right? And don't define it as tension and compression, then how would I, that's the question, how would I write this? I couldn't write it, like if I drew it in, I would have written Fe sine theta minus, Fe sine theta plus 30 plus 18, if I had drawn it as compression, right? And if I draw it this way, I draw it the other way. Either way, you get the same final result in the same direction. But if you don't have a direction, then you can't sum, just like summing moments here. If I hadn't drawn f of Fe to the right, I couldn't have summed moments of that here. I wouldn't have known how to do that. But yeah, you absolutely need to define a direction. And it doesn't matter which way. Like, don't spend too much effort thinking about it. I have a lot of background in it, so I'm kind of used to, I can take a quick look and usually get it right, but sometimes I'm wrong, like 5 or 10% of the time. That's fine. But what I mean by wrong is that the calculation shows it's negative instead of the direction initially assumed. Usually just by glancing at it, you can see which way. Not always. Okay, and then the last equation available is summation of forces in the x is 0. F of HI here, that's to the left, drawn it as compression. And this equals F of FE, so it's 40, plus the horizontal component of that 80. Four kips, and it's in compression. Now let's do section 2.2 right below that. So that's section 1.1. We took a cut all the way through the structure. We sliced through 3 different members in order to do that. And then that you have to cut through, as I said before, the members of interest. Now let's go to 2. This is a diagonal cut. We have 30, 18, these distances are 12. Height is 9. So we have F of HI. F of ED. F of EI. And this is angle theta. Oh, we also have 12 skips here. Since we're cutting just to the right of E, this 12 is applied right. So 30, everything included from the left up to the location of the slice. There's 30, 18, 12. So you see a lot of forces collected going right through E. So we can say, in order to solve for F of HI, we'll do that first by just summing moments about E. That's the simplest, right? So we have summation of moments about E equals 0. You can see the clockwise moment about an axis coming out of the page at E is F of HI. Multiplied by 9. That's clockwise, that has to equal the counterclockwise moments from the 30 and the 18. 30, I'm summing moments by E, so the 30 is multiplied by the length of 24. And the 18 is multiplied by F of HI equals four kips, compression. Again, method of sections, notice how we're, like this section cut wasn't dependent on the prior section cut. It's not like the method of joints where we're going from one to one to one. We're just here taking some example different section cuts, but, and we didn't need to start, let's say at this point and go from joint to joint to get there. That was summation of moments about E. Even this 12 kips, that applied force goes right into E, so that's not included in the summing of moments. Now let's take a summation of forces in the X is 0. I'm going to solve here for F of ED. F of ED is at an angle, so take that into account. That's our unknown in this equation. F of AD is the cosine of theta. That gives me the horizontal component to the right. All the other forces go to the left that are in the X direction. So that equals the 12 that's being applied plus 104. Hundred 45 kips in tension. And that 145 is acting along that diagonal. That's 145 kips this way. And then the only other equation available to us from statics are summing forces. So I have F of EI up. That's this force here. Equals everything down. We need to include the component, the vertical component of F of ED. So I have 30 plus 18 plus this 145 multiplied by sine of theta. 35 kips. This one. In compression. You can see its compression is pushing out. This F of H I was compression pushing to the left, so they're pushing out towards the joint. In this case, it's left, this case up. The member itself has to be in compression. This member is in tension. So that's all three forces. Then section 3.3. Now we have the horizontal cut, and it's just above C and J. So instead of going from here to here, we're going to go from here up to that point. Okay. 16 feet high and 12 feet high. Same phase. Now we need to include the reactions in the summation of this section. Solve for, the first one we'll do is we'll solve for F of Ji, and seeing that we have this diagonal force that goes right through the point P, that's above, 9 feet above where we took the section, and this F of CD also goes through there, that we can take advantage of that static force at wherever we want to sum. So we have, I'm going to sum moments about this location that's off of the section to simplify it. Okay. So I have summation of moments about V is 0. Way up there, that's why I do that point. So I have F F of ji multiplied by 12. That's counterclockwise. And then I'm just looking, so I have this force times that distance counterclockwise along the D. I don't have to include this 112, because that also goes, the line of action goes right through D. But I do need to include the 12, so you got horizontal force. And 12 multiplied by the distance to the top, which is 16 plus 9, that's 25. So it's plus, that force times the distance to D, that's also a counterclockwise move, right? So this is plus 12 multiplied by 25 equals everything going the other way. There's only one other force that's contributing to the moment. This is 160 multiplied by 12. That's clockwise. So that's 135 kips. The same compression as indicated in the original arrow. So that's the force. Summing forces horizontal. We have, this will give me F of JD, other than the reaction to the right of D. F of JD is the only thing producing, in this section, a horizontal force. I have F of JD multiplied by the cosine of theta. So that's the horizontal component of this unknown F of JD. So that's to the left, has to equal everything to the right, which is from this reaction. Kips in compression. This is 15. The compression is indicated by the way that the member has compression. So F of JI is the compression, F of JD is the compression. I've assumed based on my sketch F of CD is the tension. See if that's correct. Summation of forces in the Y. Our last equation available to us is 0. So I have F of CD that's up, right? Plus 160 is up. That's the reaction to the left. This plus this equals the force down on the right, the reaction on the right side, 112. That force plus F of JI, it's 135, that's down, pushing down. And then there's also a vertical component from the F of JD, which we know is 15, so it's plus 15. Multiplied by the sine of theta, that gives me the vertical component of that. 15. positive numbers, consistent. That means the force, the way I drew it was the correct direction of the force. It's 96 kips. Intention. Does anyone have any questions about this or moments, we're taking sections in general or method of sections? I'm gonna move on to something else. So we're going to talk now about the important topic of moment of inertia of areas. So we already have learned about centroids, how to find centroids, but you need to be able, part of the reason we do that is we need to calculate moments of inertia. It's important in statics and dynamics. The moment of inertia about the x-axis is the integral of y squared dA, and then the moment of inertia about the y-axis is the integral of x squared dA. Let's just draw a rectangle here. Rectangle has a width of b and a height of h. This is the differential area there. So we go up y. This is dy. And this area is dA. dA equal to b dy. Differential area is b dy. You can also have a differential area like this. Distance x dx, and in that case, dA is written as h dx. the upper side is defined by that equation. So imagine a piece of wood cut with this, so you have this solid piece now, right? This area. And we can calculate the centroid, we've done that before, and now we want to calculate what the moment of inertia is about the x-axis. Ix is the integral over the area, y squared dA. So let's go up. Let's say we have this. This is my W. This is my differential area. So I'm going up y. It's going up from here to this point. And this is dy. That, and the width is W. This width. This is dA. So we have dA is W dy. So this is equal to the integral over the integral of y squared W dy, which was dA. So now I'm integrating on y, the limits change where it becomes from 0 to h. This is dA. X squared is y over c. X is the square root of y over c. So for a given y location, as we're going up, that's the if we come up, let's say here, x, we're at a given y position. So knowing y, we know x. The reason that's important is this distance from here to here is W, which is also B minus that x. So we have W is B minus x, or W is B minus the square root of y over c. We have dA is W dy, so that is equal to B minus the square root of y over c dy. Ix is the integral from 0 to h, y squared of W dy, which is bracket B minus the square root of y over c dy. It's the integral from 0 to h, dy squared, bringing the y squared in, minus y to the 3 halves. No, y to the 5 halves over the square root of c. dy. So from that we get b y to the 3rd over 3 minus y to the 7 halves over 7 halves square root of c from 0 to h. This is b of this is seven halves. And then the c was, we found before, the c was h over b squared. That's just a constant parabola. So we end up with, this is b h cubed over 3 minus 2/7 b h cubed. Yeah, I was confused at first because the h's, these have to be, once we're in h, these have to be the same power, but then I remember, oh yeah, the constant has an h in it, h in it. So once I do that, then this collapses back to h cubed, bh cubed, that's a bh cubed, then you can add them together. Otherwise, it's, you know, adding oranges and apples. Okay, and so finally we get bh cubed over 21. Any questions? It's clear? That's it. Tomorrow we'll talk about what may or may not be on the exam, so remind me tomorrow. Tomorrow's Tuesday, the exam is on Thursday. And the homework is due Tuesday night, tomorrow. It's on, it says.